When I say that we are looking too far into the universe, I do not mean that we have crossed some forbidden line. I mean that our instruments now reach into regimes where our common sense fails. We are looking across billions of light years and billions of years of time. We are watching the universe when it was a fraction of its current age. And at those scales, the rules that feel obvious to us on Earth stop being reliable. To make sense of what we see, we need to trust physics, not intuition. Let me start with a simple idea. When we look far in space, we look back in time. Light travels at a finite speed, about 300,000 kilometers per second. That is fast, but not infinite. Light from the sun takes about 8 minutes to reach us. Light from the nearest large galaxy, Andromeda, takes about 2.5 million years. When we look at a galaxy 10 billion light years away, we are seeing it as it was 10 billion years ago. So our telescopes are not just looking far, they are sampling different eras of cosmic history. That simple fact is the backbone of modern cosmology. It lets us test our models of the universe's evolution. If our theory is right, then distant galaxies, which we see in the past, should look and behave differently from nearby galaxies, which we see in the more recent universe. Their distribution, their motions, their chemical content, their shapes, all of that becomes data about how the cosmos has changed over time. But to interpret what we see, we need a framework. That framework is general relativity and the standard model of cosmology, often called LIL-CDM. LIL stands for the cosmological constant, our simplest model of dark energy. CDM stands for cold dark matter. Together with ordinary matter and radiation, these ingredients shape spacetime and drive the expansion of the universe. The story starts with gravity. In Newton's picture, gravity is a force that pulls masses together. In Einstein's general relativity, gravity is the curvature of spacetime caused by energy and momentum. Mass, radiation, even the energy of empty space, all tell spacetime how to curve. Spacetime tells matter how to move. On small scales like the solar system, both pictures give almost the same answers. On cosmic scales, only general relativity works. If the universe is filled with matter and energy, then on average, spacetime cannot be static. The equations of general relativity, when applied to a universe that is roughly the same in all directions and at all locations on large scales, predict that space must either expand or contract. Observationally, we see expansion. That was first measured clearly by Edwin Hubble and colleagues in the 1920s and 1930s. They found that distant galaxies are redshifted. Their light is stretched to longer wavelengths. The farther a galaxy is, the larger the redshift on average. The simplest interpretation is that space itself is expanding, and light traveling through it is stretched along with it. Today we call this relation between distance and redshift the Hubble-Lemaitre law. It is one of the pillars of cosmology. It tells us that the universe was smaller, denser, and hotter in the past. If we run the expansion backwards in time, we reach a state of extremely high density and temperature about 13.8 billion years ago. That is what we call the hot Big Bang. The Big Bang is not an explosion into empty space. It is the rapid expansion of space itself from an earlier hot, dense state. Every region was close to every other region. Then space expanded and carried matter and radiation along. Over time, the universe cooled. Protons and neutrons formed. Later, hydrogen and helium atoms formed. Gravity amplified tiny density fluctuations. Regions that were slightly denser pulled in more matter and grew into galaxies and clusters. This broad picture is supported by multiple lines of evidence. We see the cosmic microwave background, a faint glow of microwaves coming from all directions. It is relic radiation from when the universe was about 380,000 years old, when it cooled enough for electrons and protons to form neutral atoms and for light to travel freely. The spectrum of this background is almost a perfect black body, as predicted by a hot early phase. Its tiny temperature fluctuations match the pattern expected from quantum fluctuations stretched by cosmic expansion, and then evolved under gravity and pressure. We also see the relative amounts of hydrogen, helium, and a bit of lithium produced in the first few minutes after the Big Bang in a process called Big Bang nucleosynthesis. The observed abundances agree with calculations if the universe had a specific density of ordinary matter and a specific expansion rate at that time. Those values are consistent with what we infer from the cosmic microwave background and from later structure formation. So the overall framework is strong, but when we look very far, we find things that do not fit simple expectations. For example, galaxies rotate too fast. If you measure the speeds of stars orbiting in a galaxy, they move faster than they should, given the visible mass. In clusters of galaxies, galaxies move as if there is more mass than we can see. Gravitational lensing, where mass bends light from background galaxies, also reveals more mass than is visible. The cosmic microwave background and the large-scale distribution of galaxies tell the same story. There is extra gravitating matter that does not emit or absorb light in any way we have detected directly. We call it dark matter. Dark matter is not just a patch. It is woven into our best model of cosmic structure. In simulations, if we include dark matter that interacts only through gravity and maybe weak forces, and ordinary matter that can cool and form stars, we reproduce the cosmic web of filaments, clusters, and voids that we observe. The statistics of galaxy clustering, the lensing patterns, the growth of structure over time, all line up reasonably well. That is why most cosmologists accept dark matter as a real physical component, even though we have not yet identified its particle nature. We know some things about it. It must be mostly non-relativistic, cold by the time structures form, or else it would smooth out small-scale fluctuations. It must be long-lived or essentially stable, or else the cosmic structures we see would not exist. It must not interact strongly with light, or we would have seen it in electromagnetic observations. Many candidate particles have been proposed: WIMPs, axions, sterile neutrinos, and others. So far, direct detection experiments have not found convincing signals. That is a major open problem. Dark matter shapes how galaxies and clusters form and move. But it does not explain how the expansion of the universe changes over time. For that, we need to consider the overall energy content, including something even more puzzling: dark energy. If the universe is filled with matter, gravity should slow the expansion. The rate at which space expands, quantified by the Hubble parameter, should decrease over time as matter pulls back on the expansion. For decades, astronomers tried to measure how fast the expansion is decelerating. In the late 1990s, teams studying distant type Ia supernovae, exploding white dwarf stars used as standard candles, found something unexpected. Distant supernovae were dimmer than they should be in a decelerating universe. The data fit better with a universe whose expansion is speeding up. That means the expansion is accelerating. In general relativity, acceleration of cosmic expansion requires a form of energy that has negative pressure, or an equation of state that pushes space-time apart. The simplest candidate is a cosmological constant, a constant energy density of the vacuum. We call its effect dark energy. Measurements of the cosmic microwave background, galaxy clustering, and supernova all point to a universe where about 5% of the total energy density is ordinary matter, about 25% is dark matter, and about 70% is dark energy, behaving very much like a cosmological constant. In this model, the expansion was slowing down in the early universe, when matter and radiation dominated. As the universe expanded, matter and radiation diluted, but the dark energy density stayed roughly constant. Eventually, dark energy took over and the expansion began to accelerate. That transition happened a few billion years ago. Today, the expansion is in an accelerating phase. This has deep consequences for what it means to look far. In an accelerating universe, there are event horizons. There are regions of space that even if they send light toward us forever, that light will never reach us because the space in between is expanding too fast. There is a maximum distance from which we can ever receive new information, called the cosmic event horizon. There is also a maximum distance from which light has had time to reach us so far, called the particle horizon. The observable universe is limited by these horizons, not by our technology. Right now, the radius of the observable universe, the distance to the farthest regions whose light has just had time to reach us, is about 46 billion light years, even though the universe is 13.8 billion years old. That mismatch arises because space has been expanding while the light traveled. But beyond a certain distance, galaxies are receding from us faster than light, not because they are moving through space faster than light, but because space itself is expanding. In general relativity, that is allowed. The speed of light limit applies to motion through space, not to the expansion of space. So when we say we are not supposed to look this far, one interpretation is that the universe sets absolute limits. There are regions we can never see, no matter how advanced we become. There are events whose light will never reach us. We are confined to a finite observable patch. The rest of the universe, if it exists beyond that, is causally disconnected from us. This is not a philosophical boundary. It is a physical one, encoded in the geometry of space-time and the presence of dark energy. We can write down the metric that describes our universe on large scales, usually the Friedman-Mate, Robertson-Walker metric. We can solve the Friedman equations, which relate the expansion rate to the energy content. From those, we can compute the horizons. The result is that in a LCDM universe, the event horizon has a finite radius on the order of tens of billions of light years. Beyond that, events are forever outside our future light cone. This changes how we think about cosmic destiny. In a universe without dark energy, or with enough matter to eventually halt and reverse the expansion, the ultimate fate could be a big crunch. In that scenario, the universe would recollapse, structures would fall together, temperatures and densities would rise. But in our observed universe, with a dominant cosmological constant, the expansion will not reverse, it will continue to accelerate. As time goes on, distant galaxies will cross our event horizon. Their light will redshift to longer and longer wavelengths until it is effectively undetectable. They will fade from view, not because they stop existing, but because space-time stretches so fast that their photons cannot keep up. In the far future, only the gravitationally bound structures, such as our local group of galaxies, will remain visible to each other. Even those will merge over time into a single large galaxy. The cosmic microwave background will redshift to wavelengths larger than the size of our galaxy, becoming undetectable. Future observers trillions of years from now might not be able to reconstruct the Big Bang from local observations. The evidence will be diluted by expansion. So there is a sense in which we live at an interesting time. The universe is old enough that complex structures, stars, planets, and life have had time to form. But it is not so old that cosmic acceleration has erased the large-scale evidence of its origin. We can still see the cosmic microwave background. We can still see galaxies billions of light years away. We can still measure the Hubble expansion on large scales. Our window is finite in both space and time. Now consider what our modern telescopes are doing. Instruments like the Hubble Space Telescope, the James Webb Space Telescope, large ground-based surveys, and cosmic microwave background experiments are pushing our view to redshifts of 10, 12, maybe more. That corresponds to times when the universe was only a few 100 million years old. We see galaxies forming, stars igniting, black holes growing. In the cosmic microwave background, we see back to 380,000 years after the Big Bang. In principle, with gravitational waves and neutrinos, we might probe even earlier eras. Each step pushes our understanding of physics under extreme conditions. But the farther we look, the more our naive expectations fail. For example, the distribution of galaxies on very large scales is not random. It forms a cosmic web, filaments, nodes, and voids. This pattern reflects the growth of tiny initial perturbations under gravity in an expanding universe filled with dark matter and dark energy. We can measure the statistical properties of this web, such as the power spectrum of density fluctuations. Those measurements match predictions from the LCDM quite well on large scales. On smaller scales, there are tensions. The number of dwarf galaxies, the inner density profiles of dark matter halos, and some aspects of galaxy formation are still being actively studied. We also see hints of tension in measurements of the expansion rate today, the Hubble constant. Local measurements using supernovae and other distance indicators give a value somewhat higher than the value inferred from the cosmic microwave background under the LCDM model. This Hubble tension might be a sign of unknown systematics in the data or analysis. Or it might point to new physics beyond the standard model, perhaps involving dark energy that evolves with time, or extra-relativistic species in the early universe. At present, we do not know. The data are improving and theorists are exploring possibilities, but there is no consensus. Dark energy itself is another major unknown. The cosmological constant is a simple fit to the data, but when we try to understand it from quantum field theory, we run into a huge problem. Quantum fields in empty space have zero-point energies. If we sum those contributions up to some high-energy scale, we get a vacuum energy density that is many orders of magnitude larger than what we infer from cosmology. The observed dark energy density is tiny compared to naive theoretical expectations. This is the cosmological constant problem. We do not currently have a widely accepted solution. One alternative is that dark energy is not a true constant, but a dynamic field, sometimes called quintessence. In that case, its energy density and pressure could vary over time and space. That would change the expansion history in a measurable way. Surveys of supernovae, baryon acoustic oscillations, and weak gravitational lensing are trying to constrain the equation of state parameter W, which relates dark energy pressure to its energy density. So far, W is consistent with -1, the value for a cosmological constant, within current uncertainties. But the error bars still allow small deviations. Future surveys may tighten those constraints or reveal evolution. Another possibility is that our theory of gravity itself needs modification on large scales. Perhaps general relativity is not the full story in the low curvature, large distance regime. Many modified gravity models have been proposed. They must reproduce the success of general relativity on solar system scales and in strong field tests, such as binary pulsars and gravitational waves, while changing behavior on cosmological scales. Most such models are tightly constrained by current data. None has yet clearly outperformed LCDM with a cosmological constant. But the door is not fully closed. When I say we were never supposed to look this far, I am also pointing to the fact that our brains evolved to handle everyday scales, meters, seconds, kilograms. We did not evolve to think about gigaparsecs, billions of years, and the curvature of spacetime. Our intuition is tuned to a nearly flat, slow, low-energy environment. On cosmic scales, spacetime is curved, expansion is significant, and the dominant forms of energy are invisible. So we have to use mathematics and observation to extend our understanding. We must accept results that do not feel intuitive, but are supported by evidence and consistent theory. For example, the idea that most of the matter in the universe is dark and most of the energy is dark energy is deeply unintuitive. Yet multiple independent observations converge on that picture. Galaxy rotation curves, cluster dynamics, gravitational lensing, the cosmic microwave background, large-scale structure, supernova distances, and more. Each line of evidence has its own systematics and uncertainties. But together, they form a coherent framework. When a theory explains many different phenomena with the same parameters, that is a strong sign that we are on the right track. At the same time, we must be honest about what we do not know. We do not know the particle nature of dark matter. We do not know the origin or microphysical explanation of dark energy. We do not know whether the cosmological constant is truly constant or only approximately so. We do not know if the Hubble tension is new physics or subtle bias. We do not know what happened at the very earliest moments of the universe, near the Planck time, when quantum gravity effects would be important. Our current theories, general relativity and quantum field theory, are not yet unified in that regime. We also do not know the full global structure of the universe beyond our observable patch. The observable universe may be just a small region of a much larger whole. That larger universe could be finite or infinite. It could be topologically simple or complex. It could have different properties in distant regions, though our current observations suggest large-scale homogeneity and isotropy within our horizon. Inflationary models, which propose a rapid exponential expansion in the very early universe, tend to produce regions far beyond our observable horizon. Some versions even predict a multiverse with different physical conditions in different regions. Those ideas are speculative and hard to test directly because, by definition, regions beyond our horizon are causally disconnected. We must be careful not to overstate what we can know. What we can do is push our observations to the edge of our horizon and test our models as hard as possible. The cosmic microwave background has been mapped with high precision by missions like WMAP and Planck. Its temperature anisotropies and polarization patterns encode information about the early universe, the matter content, the geometry, and the expansion history. Large galaxy surveys map the three-dimensional distribution of galaxies over billions of light years. Weak gravitational lensing surveys measure the subtle distortions of galaxy images caused by intervening mass, probing the growth of structure. Supernova surveys measure the expansion history directly. Gravitational wave observatories open a new window on compact objects and potentially on the early universe. Each of these tools lets us look far in a different way. Far in distance, far in time, far in energy scale. Together, they form a cross-check. If our model fails, it must fail consistently across these different probes. So far, LCDM with general relativity, cold dark matter, and a cosmological constant has survived many tests. But the tensions and unknowns I mentioned are real, and they are where progress is likely to come from. There is another subtle way in which we might be pushing too far. When we extrapolate our current laws of physics to conditions we have not directly tested, we assume that those laws hold universally. That assumption has worked very well. The same physics explains nuclear reactions in the sun and in distant stars. The same atomic physics explains spectra in laboratories and in quasars billions of light years away. The same general relativity describes the orbit of Mercury and the merger of black holes at cosmological distances. But at some point, new phenomena may appear. For example, at very high energies, near the Planck scale, quantum gravity is expected to become important, and our current theories are incomplete. In cosmology, this appears when we talk about the initial conditions of the universe. Inflation is a leading idea to explain why the universe is so uniform on large scales, why it is nearly flat, and why the initial perturbations have the observed spectrum. Inflation posits a period of rapid accelerated expansion driven by a high-energy field. That idea fits the data well. But we do not yet know the detailed physics of the inflationary field. We do not know what happened before inflation, or whether that question even makes sense in our current framework. We can infer some properties of the early universe from the cosmic microwave background and large-scale structure. But there is a limit to how far back we can see, set by the opacity of the early plasma and by the breakdown of our current theories at extreme energies. So we are in a situation where we have a remarkably successful model for the universe from about a fraction of a second after the Bang to the present and into the future, given the current energy content. But we lack a fundamental understanding of key ingredients and of the very beginning. That tension is productive. It tells us where to look next. As our telescopes and experiments improve, we will refine measurements of dark energy's equation of state. We will search for dark matter particles in underground detectors, in colliders, and in astrophysical signals. We will map the large-scale structure more precisely. We will detect more gravitational waves, perhaps even a stochastic background from the early universe. We will test general relativity on larger scales and in stronger fields. Each of these efforts pushes our view further, not just in distance, but in understanding. The phrase, "never supposed to look this far," can sound like a warning, but in science it is an invitation. It reminds us that our intuition will be challenged. It reminds us that nature is under no obligation to be simple or satisfying. It reminds us that our current picture, while powerful, is provisional. We should trust the data, trust the mathematics, and be ready to revise our ideas when new evidence demands it.